your slides are now showing, and a small kind of preview of you as well. Let me expand that so they can see you a bit better. There we go. Cool. There's J vector. There's a John. Does the J stand for John?
Or John? Stands for Java.
Oh, right.
but the three authors are Jonathan, Jake, and Joel. So maybe it does stand for our names as well.
Cool. Cool. Yeah. So take it away, because I think everything is all good to go.
All right. So yeah, I've been working in the database space for 15-ish years, and I've been working on the vector search space for just about 6 months. And it's really cool how fast this area is moving. So just to bring us back down to all on the same page, vector search is how we do the retrieval in Retrieval-Augmented Generation. So we need to give the AI some context so it can stay grounded and not hallucinate. We've got a data source, but we need to surface what pieces of data are the most relevant because we have a limited context window to give to the LLM. So I'm just going to wave my hands here and say we have this magic thing called an embedding model that can give us a vector that represents any arbitrary piece of text. And in practice, there's a limited size to the text you can give it. It's usually 512 tokens or 1024 or up to 4K. But there's a fairly limited size of tokens, so you're talking about a few sentences or a paragraph. You're not generally going to be throwing entire articles into this, but that's okay. You can break up large articles into multiple chunks, compute the embeddings for each chunk, and then say, hey, which article is associated with the most relevant embeddings? So that's what vector search is about, is given a query or a question or something that I want the LLM to engage on, how can I find relevant context from a large corpus of data to give to the LLM? So the classic posing of this problem is called KNN, for the top K nearest neighbors. So tell me not just the closest single vector, but maybe I want the closest 5 vectors. So that's going to be my K in KNN. And the problem with this is, and the reason that this is so interesting, is that nobody knows how to do this efficiently to give exact answers. You can do it in 2 dimensions or in 3 dimensions, but the algorithms that let you subdivide those spaces into quadrants or into hypercubes, those get exponential in the number of dimensions of data that you have. And the embedding vectors generated for AI models are going to be, a small one is 384 dimensions. The most popular one right now is OpenAI's Ada 002, which is 1536 dimensions. Google's Gecko model generates 768 dimensions, so kind of splitting the difference there. So we've got hundreds of dimensions that we need to worry about, and so we don't know how to do this in linear time. So the question is, how can we do approximate nearest neighbor? So that's what the A in ANN is, approximate. How can we do that in logarithmic time? Ideally, you want your searching to be log of n, log of the number of vectors you have to search. And we have 2 broad approaches that researchers have come up with to answer this question. So I've represented each of those categories here on this slide. So on the left, we have the partitioning approach. So this is a 2D diagram of a Voronoi field. And what the Voronoi field is for every point that I'm storing, I will have a polygon representing the other points in 2D space that are closer to that data point than to any other. So if you look at those polygons and start to think like what's the distance to any of the other red dots, then you'll see how that works. And this generalizes to multiple dimensions. So one of the most popular approaches to partitioning, it's not the only one, but it's one of the most popular, is called inverted Voronoi field, where you basically partition the vector set into these Voronoi areas, and then instead of searching the entire set of vectors, instead of doing a comparison against each vector to find the closest ones, you'll take the closest polygons to the query vector, and then you'll just search those. So that can cut down your search time significantly. The other main approach that people use is graph-based indexing, where you construct a graph of your data set and you select edges between each vector and some of the other vectors. And how exactly you select those edges, that's the difference between a good graph index and a poor one. But the idea is you've got this graph, and then you can just do a simple breadth first search with a greedy selection algorithm to find the approximate closest neighbors to your query. So if we look at, there's a website called annbenchmarks.com. There's a GitHub repository associated with it. And it's basically the place where vector search researchers try to one-up each other and come up with better solutions. So there's 50-ish algorithms on ANN benchmarks, but I've selected for this slide, I've selected one of the data sets that has a relative few number of contestants. So we've only got 10 or 15 different algorithms here. And I'll show you how we can split up those algorithms into the two categories that I just showed, the partitioning based and the graph based. So the first thing we're going to do is we're going to just throw away the bottom 5. So the bottom 5 are these, and these are all basically obsolete now, and that's why they're on the bottom. So Annoy is a tree-based approach, for instance. None of these are something that you would build a new system based on today. So then the next ones that are performing well, so these are the partitioning-based contestants for this data set. So we've got Scan from Google Research, and then we've got basically Facebook's equivalent of Scan out of the Face library. And then everything else, all the other entrants here are graph-based. And in fact, all of these graph-based algorithms are using a single kind of graph index, and that's called HNSW. So Phil mentioned that this is a popular place to start because it is fast and it's simple. Like those are really good virtues. And also, by the way, looking at the names here, I'll go back here. So you see Milvius, you see Glass, which is basically the embedded engine behind Milvius. You've got Weaviate, all of the, this one, this is like some research projects. This one is commercial products. So why do the commercial products reach for the graph side instead of the partitioning side? And it's because you can construct the graph index incrementally. You don't have to wait for all of your vectors to be ingested, and then now that I know what the vectors are, now I can partition them, compute the centroids, and so forth. With the graph-based algorithm, you can build the index as you're adding vectors to the data set, and if you do it correctly, then you can do searches concurrently while the index is being constructed. Lucene uses HNSW, Weaviate does, Quadrant does, PG Vector does, and like I said, everything on that slide also used HNSW. So the idea with HNSW is there's an older paper called NSW, Navigable Small World, and it talks about how you can build a graph based index. However, NSW had a problem, which is that your searches would tend to get stuck in local maxima. And there were actually vectors that were closer, just a little bit farther away, but you didn't see them because you thought you were in this really good spot, and the greedy algorithm kept you stuck there. And so to avoid that, what HNSW does is it adds the H part, which stands for hierarchy. And so what we're going to do is, besides the main index at the bottom, we're going to add additional layers. And the first layer, we're going to take just 10% of the vectors. Each vector has a 10% probability of being added there. And then the next layer up, each vector has a 1% probability. The next layer up, a 0.1%. So you've got these smaller subsets of the vectors that you can navigate through very quickly, find the best place in that subset, and then find the corresponding one of the next layer down and start your search from there. Find the corresponding one on the next layer down, restart your search from there. And so what that does is it means that the upper layers have increasingly long edges between the vectors. So you're kind of skipping over large parts of the graph to find the right location to search from. And that means that you have a much, much lower chance of getting stuck in those local maxima. And so your search gets faster, which is good, and it gets better results, which is even better. So that's why it's so popular. However, there is a known downside to HNSW that we ran into when we built our first public vector search product on top of it. And that is that HNSW requires a lot of memory, because every time that I'm going between these nodes in the graph, I need to compare the query vector with the node that I'm exploring to see if I've gotten closer or farther from where I want to be. And so doing those comparisons, if those vectors are on disk instead of in memory, it's just brutally slow. Because in a normal database workload, we're used to being able to say, oh, hey, Pareto principle, 80% of our data or 80% of our queries only care about 20% of our data. So we can just rely on caching to handle that. And we can have data sets that are larger than memory, but it's okay because the hot data still fits in memory. That doesn't work with vector search, because each node in the graph, each vector, has roughly equal probability of being touched by any query. So what we found is when we did a flame graph profile of doing a search against an index with 100 million vectors in it, is that there weren't any flames. There's just this one big chunk. And hopefully you can read that in the audience. But what that's saying is the top tan line here says random access reader.read floats at. So, and then the rest of it is just JVM code to read bytes off of disk. So what that's saying is that like 95% of our query time was spent pulling those vectors off of disk. I neglected to say that 100 million Wikipedia vectors was something like 80 gigabytes of memory, and we're trying to serve this from 32 gigabyte cloud VMs, so it didn't fit in memory. That's what happened. So there's a couple approaches to tackling this from the research community, and I flipped the order on this slide. I apologize. So in this slide, the graph-based approach is on the left and the partitioning-based approach is on the right. For graph-based indexes, Microsoft Research has a paper about an approach called DiskANN. And then also from Microsoft Research, but from a different team, a partitioning-based approach called SPAN. So I took a quick look at both of these when we were evaluating, like, how do we serve larger than memory vector indexes for our Astra service. And I ended up going with the disk-ANN approach, which might be a little bit confusing if you are very fast at reading and you notice in the bottom right side of the span page, it says, experiment results demonstrate that span is twice as fast as disk-ANN. And so like twice as fast, that's good, right? But however, having implemented a graph-based HNSW index, it was a much smaller step for us to move to disk-ANN. And disk-ANN is public. Like it's not just like a research paper, but Microsoft has a disk-ANN repo on GitHub, and it's used in production in Bing. So it's not like 4-year-old code and then we forgot about it, but we can actually go through. We as members of the public, we can go through and look at, oh, hey, what improvements did Microsoft make to disk-ANN after publishing the paper? And that turned out to be really useful for building our own implementation. So that's why we went with that. So disk-ANN proposes 2 or 2.5 changes to the HNSW approach, depending on how you count. So the first one is that instead of doing hierarchical layers in the graph, disk-ANN says we're going to use an algorithm we call Vimana, and we're going to allow the graph to add longer edges, but keep it in a single layer. And so on the left, this is what an HNSW layer would look like. Going back to that navigable small world paper, it really tries to keep the degree of the graph small and only add edges that are going to connect to different parts of the graph. And so Vimana relaxes that and says, in the interest of adding those longer edges that let us skip between different parts of the graph and get out of those local maxima, we're going to relax that in a specific way, in a controlled way, to enrich the graph. So that's idea number one. The main thing that does, the performance is basically the same. You search both of these graphs with a greedy breadth first search, and the performance, sometimes one is better, sometimes HNSW is the better, but it's always within like 1% of each other. It doesn't make a whole lot of difference. However, it simplifies the implementation of the next part dramatically, and that's where the big win is in disk-ANN. And that's with doing product quantization. So rather than doing each comparison with the full vector, disk-ANN says, hey, let's compress the vectors using this idea called product quantization that's been floating around the machine learning community for a while in other contexts. And we can actually compress our vectors down by a factor of 8 or 16 or even 32 and keep them in memory, keep the compressed version in memory, because, hey, I can afford to keep 1/16 of my vectors in memory. I just can't afford to keep the entire thing. And then I can do the comparisons using the compressed version. So the way product quantization works, like the super quick version is, I'm going to break up that monster, 768 dimension vector into 8-dimension chunks. And then for each of those chunks that I've labeled D prime in the diagram, I'm going to build a code book of the 256 most interesting or most spread out points across all of the vectors in my data set. So I'm going to represent that 8-dimension chunk in a single byte. That's basically just an index into this table of which code point is that 8-dimension chunk closest to. So for each sequence, so for the first 8 dimensions, then the second 8 dimensions, the third 8 dimensions, I'm building a different 256 point code book. And then I'm storing indexes for each vector by those chunks into that code book. And so I can actually do a comparison against an uncompressed query vector using my codebook without ever having to decompress it. So my searches get faster, but they get less accurate. And the way we get around that is, I'll get to it in just one more slide. But before I do that, here's one more idea, which is instead of doing product quantization, we can do binary quantization. Binary quantization is a different kind of compression where instead of building a code book and instead of allowing to compress by an arbitrary amount, binary quantization is just a fixed 32x compression where I'm going to take each of those float 32 values in the original vector. And if it's positive, then that becomes a 1. If it's negative, it becomes a 0. That's it. Like that's the entire compression algorithm. So it turns out that if you do a search with product quantization instead of the full uncompressed vector, then you lose, depending on the data set, you lose between 5 to 15% recall. So it's not zero. It's not zero. And with binary quantization, you're probably going to lose between 15 and, if we're going to say we're restricting it to data sets that are appropriate, then you lose between 15 and 25%. So you lose even more. So you're like, wow, like that's a lot of recall to lose. Like, I'm not sure that's a good trade-off. However, because both of these compression designs let you search faster, you can trade some of that search speed to look deeper in the graph. And that's called oversampling. So what that's saying is instead of searching for just the closest K, I'll search for instance, I'll search for 2K, twice as many. And then I can read the uncompressed vectors from the disk during the search whenever I add a candidate to the result set. And then when I'm done with the search, I'll reorder that result set by the uncompressed vector comparisons and then return the top K. And so what that does is, if I'm doing like the 2x example, that's a nice round number, but it turns out that's about how much you need to search extra when doing product quantization to make up completely for the loss of recall that you had. And so, so now I've got a design that it's saving me a ton of memory, making my searches faster, and I'm not losing accuracy. It's basically a free lunch. And so I'm going to talk about JVector in just a second. The oversampling code doesn't live in Cassandra. It doesn't live in JVector. It lives in Cassandra. But this is what that looks like. It's fairly simple. And basically, it's saying that if you give me a smaller K that you're interested in, I'm going to increase the oversampling by more to make sure that I'm still giving you a high recall result. And then the rest of it is pretty straightforward. So JVector is the embedded library that we've built. It's a Java library for vector search. And the closest alternative, I mentioned earlier that there's a whole bunch of products built on Lucine's HNSW search. So JVector's an embeddable Java library, Lucine's an embeddable Java library. They're pretty apples to apples. So what I did was I built an index of the deep 100 million data set. So what I did was to do this, I built the index on a cloud VM with a zillion gigs of memory. And then I downloaded it to my laptop, which does not have a zillion gigs of memory, so that I can highlight the difference when you are doing searches against a data set larger than memory. So JVector is roughly 15 times faster than Lucene in this scenario. I didn't bring a separate graph, but when you're just searching in memory, then it's still 3 to 5 times faster because of the quantization that it's doing. So that's relevant in memory, but it's very relevant out of memory. Now, Phil mentioned at the beginning that doing a pure vector search, that's interesting, but being able to combine the vector search with other query predicates, like that's way more interesting. So for instance, if I have this table of hotels and each hotel has a coordinate, and I'm representing the latitude and longitude as a two-dimensional vector, and then I have a description of that's a 1536 dimension embedding vector, I can search for hotels within 10 kilometers with the first predicate here, where geodistance. That's saying search for points within 10 kilometers. And then I can order those hotels by their vector similarity along that description embedding. And the interesting thing about this is you can do, there's actually 3 approaches that you can take. And I can give examples of production systems that use all 3 approaches. So it's not like, oh, one of these approaches is obviously good and the others are bad. There's pros and cons. So the first one is to post filter. So that in this design, you do your vector search first, you get back your top K, and then you apply your Boolean predicates to the top K results. So I said there's benefits to each of these, but I think this option is the worst. Pinterest used to do it, but they moved away from it because you kind of have to guess like how many of those, if I want 100 results and I think my Boolean predicates are going to reject 60% of them, then I actually need to bring back 180 queries, 180 results out of my ANN index. And so, and if you get it wrong, then you have to go back and try again. The main advantage, I will say the main advantage is that it is straightforward. It does have that going for it. I think a better option is to pre-filter. And that means that you're going to compute the result set of your Boolean predicates first, and then you'll tell your ANN index, restrict your results, restrict your answer to only vectors that match these IDs that I'm giving you from the pre-filtering. And that's what Cassandra uses. That's what we're doing in Astro. And then the third approach is to say, hey, we'll just evaluate them at the same time while we're doing the vector search, while we're doing that greedy breadth first search, and we're evaluating nodes. Part of our evaluation will be, hey, does this node match these other predicates? Like we'll look up the metadata associated with it, check the other predicates, and see if that works. And so if you're going for kind of a pure vector index approach, you're going to tend to be oriented towards the right side. I say tend to because all the pure vector databases that I can think of take this approach, but I'm not going to say it's impossible for them to do something different. But that's the ones that I'm familiar with do follow that. But here's the downside to that. The downside to the stream filtering is that you have the needle in a haystack problem. And I don't know I don't know what the term of art here is, but what I mean by that is if you have, let's go back to my hotels example. So if you have, if you're searching for hotels near Papeete, Tahiti, population 30,000, then there might be 15 hotels in your data set within that geo distance. And then if you've got 1 million vectors in your index, and then you're saying, I'm only interested in hotels that are part of this group of 15, and I want you to rank those 15 by the embedding distance, then you're going to have to scan basically the entire index to find those 15 hotels before you can rank them. And so what this graph is showing is on the x-axis, the top k-axis, as we move toward the right, we're asking for more results. And then the candidates axis on the y, as you move towards the front, then you're giving the index more candidates to choose from. So you're saying, I've restricted it to 100,000 hotels. That's like that's the lowest point. in the bottom right. And then in the back, I've restricted it to just a handful of hotels. So this data set, this is the New York Times article vector embedding data set. It's 290,000 data points. And what we're graphing here on the z-axis is the number of nodes visited to find K results within B candidates. So you can see that as the number of candidates goes towards 0, the number of nodes visited goes towards 290,000. And so what we do in Cassandra, this is why we take the pre-filtering approach, is we'll evaluate those predicates before the vector index search. And if that is going to result in a ton of nodes visited, then we'll just do a brute force in memory and do a linear comparison of all of the results rather than going to the vector index, because the vector index is actually more expensive. And so what does a lot look like? Well, that depends on the data set. So it turns out the formula this is the best that we've come up with. It's possible that there's a better one, but the best we came up with, it's proportional to the square of the log of the number of vectors in the index. And it's also proportional to the square of the log of the ratio of the number of nodes in the index to how many candidates there are. In other words, the more you restrict the candidate set, the more that term explodes. But when you plug the different data sets into this formula, we get something that looks pretty linear, which is what we want. That means that we can give a pretty accurate prediction of whether it's going to be more expensive to search the index or to just brute force all the results. So like I said, I've been doing this for 6 months. So I've learned a bunch over that time. So here's some of the things that I learned that were a little bit surprising. We already talked about this at length. HNSW really is slow if it doesn't fit in memory. And we just talked about how it can be faster to just not use the index if you have a pre-filtering design. And then the last one is 2 months ago when I gave a talk like this. My last thing that I would say is OpenAI embeddings are really huge, and huge means slow. Therefore, you should use a more compact embeddings model. And there's a bunch of open source embeddings models that are competitive in recall with OpenAI's embeddings that are much smaller. So I would say go use one of those. However, now that I've learned about binary quantization and we've implemented that in Astra, now I have modified that to say even though they're so over parameterized, they're so large, but when I compress them with binary quantization, which Astra does automatically, it's so fast that go ahead and use them. So back where we started in a way. Finally, you can get JVector from GitHub at this URL, and we have our hosted vector search at the second URL. Now, I hope I answered the questions I heard during Phil's talk. I heard some questions that Phil said, oh, Jonathan's going to talk about that. But I didn't actually get to hear the actual question, so I'm just kind of going on faith that maybe I touched on it. So if I didn't, then I'd be happy to answer questions. Unless Matt tells me I'm out of time and we'll take this offline.
Can you hear me?
Sure can.
Oh, you can. Cool. We've only got time for one question. So first hand that goes up. Any questions? No questions. No. Oh, we got one. Yep.
Just on the benchmarks on the quantization methods. Can you touch on that? Can you?
I heard something about benchmarks. Can you repeat the question, Ben?
Could you? Sorry, I can't remember. There's such technical benchmark.
Just want to, do you have any benchmarks on the recall rate reduced because of the quantization method that you mentioned?
especially with
I
'cause-
mean, I have a zillion benchmarks of that. I don't have a slide with them, but if you check out the JVector repo, there is a sample program called Bench. And so that's integrated with the Maven build script. So you just have to say Maven exec bench. It'll go to town. It'll download data sets. And one of the things it does is it tells you it's a grid search. So you can do different parameters. And one of the parameters is how much do you want to compress? And so you can say, I want to compress it 4x, 8x, and 16x, and compare each of those results with the uncompressed recall. And so you can get the results of that pretty easily.
Cool. Thanks a lot for giving this talk. Yeah, that's all the time we had for questions. So the next. Oh yeah. So I've just got to.
Thanks for letting me join you, everyone.
I have just got to unplug you now, so so no one will be able to see you, but you can still listen in, obviously.